Hi there, this is Mr. Schnitzius, and in this video we're going to begin working through Activity 26, Lesson 26-1, and in this video we're going to focus on proving the midpoint formula. So we have two learning targets here. That's to write coordinate proofs and also prove the midpoint formula. So this means do more than just use the midpoint formula. This means prove, like show with certainty that the midpoint formula is valid. So there's a little blurb here for us to read through at the beginning of Activity 26. This is on page 373 if you're following along with your Unit 4 PDF. A coordinate proof is a proof of a geometric theorem, corollary, conjecture, or formula that uses variables as the coordinates of one or more points on the coordinate plane. Coordinate proofs can be used to justify many of the theorems and formulas you have learned so far. To form an argument using coordinate geometry, you will need to rely heavily on your knowledge of geometric and algebraic principles. So these are basically proofs where, as part of the justification for the proof, we're using coordinates of points in the xy plane. So this starts off with an example where we're using the midpoint formula. It says draw a segment AB on the coordinate plane with endpoints A at -4, 3 and B at 2, 1. They also want us to find and plot the midpoint M of segment AB and state the formula that you use to determine the midpoint. So we're going to show the work for using this midpoint formula here in just a moment. Here are points A and B. And even if we just didn't solve this with the midpoint formula, we should be able to see that if A is here at -4, 3 and B is here at 2, 1, then the point exactly in the middle would be here at -1, 2. So that gives us the coordinates for the midpoint. If you wanted to see how to work that out using the midpoint formula, then we could label our points x1, y1, x2, and y2. And let's see, that would be -4 plus 2 divided by 2. Y1 is 3 plus 1 divided by 2. So -4 plus 2 is -2. 3 plus 1 is 4. And when we do our division there, -2 divided by 2 is -1. 4 divided by 2 is 2. And so that's how we end up with the final answer. So doing a coordinate proof is different, though, than what we're doing here. It's trying to show that we know absolutely for sure that this formula works. So we're going to step through how to do that here with number 3. So if we're given not just the 2 points that we had before, but any 2 points, x1, y1, and x2, y2, and if we're given that the coordinates of M are given by this midpoint formula, we're going to prove that point M is the midpoint of segment PQ. So how do we do that? Well, we need to show two things. If point M is the midpoint, then the length of segment PM is going to be the same as the length of segment MQ. And also, the length of segment PM needs to be half the length of segment PQ, and the same thing for segment MQ. Segment MQ needs to be half the length of segment PQ. So here's how we're going to go about showing that. We're going to use the distance formula to find the length of segment PQ. Substitute the coordinates of P and Q into the distance formula and write the resulting expression. Well, usually whenever we do the distance formula, we label our points, x1, y1, x2, and y2. Those are already the coordinates that we're given, though. So this is just going to be writing out the distance formula. It's going to be the square root of the difference of the x values squared plus the difference of the y values squared. So there's going to be, this is all on page 374 of your Unit 4 PDF. I wanted to be able to go back and forth. So we're going to be flipping back and forth between these pages several times. But this right here represents the length of segment PQ in terms of the coordinates, since this is a coordinate proof of points P and Q. So that's our goal is going to be to show that the length of segment PM is half of that, and also the length of segment MQ is half of that. So we're going to start off by finding the length of segment PM with the distance formula. So this is going to be a little bit trickier because now we've got x1 and y1 for the coordinates of P, but the coordinates of M are x1 plus x2 divided by 2 and y1 plus y2 divided by 2. So we're going to plug this x value for the midpoint in first. So underneath the square root sign, we're going to put the x value for the midpoint, x1 plus x2 divided by 2. And we're supposed to subtract x1. Why? Because that's the x value for P. And the distance formula tells us that we're supposed to square that. And now we need to do the same thing for the y values. We're supposed to do the y value for point M. So that was y1 plus y2 divided by 2 minus y1 squared. Okay, so somehow or another, this expression is supposed to be half of this expression. Well, I can't see that right away, so in order to prove that, we need to simplify this expression. So it says first, use a common denominator to combine terms within each set of parentheses. Well, right now, we've got a denominator of 2 here, so that means we need a denominator of 2 here for this x1 term, and then the same thing for these y terms right here. So the common denominator that we're going to go for is 2. So for our first fraction, this is still going to be x1 plus x2 divided by 2. That's the x value of point M. But we want to have a denominator of 2 for this x1 term. If we multiply the denominator by 2, then we better multiply the numerator by 2 as well. So now we've got this expression for the x's, and we're going to have the same kind of thing for the y's. y1 plus y2 divided by 2 minus 2 times y1 divided by 2. That whole quantity gets squared. Now, what we can do, since both of these terms inside this first set of parentheses have a denominator of 2, we can go ahead and combine the like terms. We can combine this into a single fraction with a denominator of 2. So we're going to go ahead and do that. And when we do that, this is going to give us positive x2, and we have x1 minus 2x1. Well, that's going to be negative x1 minus 1x1, but we don't really need to put a 1 right there. All right, and that's supposed to be squared, plus we end up getting the same thing with the y's. So y2 minus y1 divided by 2 squared. Okay, the last thing that they want us to do is simplify so that there are no fractions under the square root sign. Now I'm going to copy this so I don't have to rewrite it onto the next page. Okay? And what we can do first here is we can say, well, if we're squaring this whole quantity, that means we're going to square the numerator, but we're also going to square the denominator. So this is going to be x2 minus x1 squared, but it's also going to be 2 get squared in the denominator. Same thing right here. We want to have y2 minus y1 squared in the numerator. And then we want to have 2 squared in the denominator. Well, this is really, really good news for us because 2 squared is really, really easy to work out. That's 4, right? So this is going to be x2 minus x1 squared over 4 plus y2 minus y1 squared over 4. And since both of these terms have a 4 in the denominator, we can factor out a 1/4 in front. And then what we'll be left with is just x2 minus x1 squared plus y2 minus y1 squared. And then we actually want to have another set of parentheses there because that 1/4 didn't just get factored out of the first term, it got factored out of both. Now, when you were simplifying square roots, when you were working through the Pythagorean theorem, you saw that if you had a square root of a product, you could break that up into 2 different square roots multiplied together. So this is really the square root of 1/4 times that expression that we have left in terms of the x's and y's. And now we should be getting pretty excited because this is exactly the same thing that we had for the length of segment PQ. And we know that the square root of 1/4 is 1/2. So since this distance formula expression is exactly equal to the length of segment PQ, remember that's what we got at the very beginning, now we've shown that segment PM is equal to 1/2 the length of segment PQ. Very good. So now we get to do the same thing for segment MQ. We're going to work that out exactly the same way. This time we're going to get that the length of segment MQ, remember point Q is the x2, y2. So we're going to do this a little bit differently. This time we're going to plug in the x2 first and then the x1 plus x2 divided by 2 second, and then y2 minus the y value for the midpoint. So we're going to plug that right on into the distance formula. So that's going to be x2 minus this quantity x1 plus x2 over 2. We're supposed to take that and square it. We want to do the same thing with the y's. The y value for point Q minus the y value for point M. Now, this might look a little messy right now, but we're going to do the algebra the exact same way. All right, so we want to have a common denominator. So for this x2 term and this y2 term, we want to have a denominator of 2. So we're going to make that 2x2 over 2 minus the x value for point M. We were supposed to take that whole thing and square it, plus same thing for the y values. All right, so what's going to happen, we're going to skip just a little bit. For this first term underneath the square root sign, what's going to happen? Well, we have 2 in the denominator for both terms. Okay, so this expression is going to be over 2. We've got 2x2 minus 1x2. Well, that's just x2. x2 minus x1, but we're still squaring that. All right, and then we want to do the same thing over here. We've got a common denominator of 2, so we're going to combine those two fractions together. 2y2 minus 1y2 is y2 minus y1. We're taking that whole expression and squaring it. All right, same thing as before. When we square a quotient, when we square this fraction, we're really squaring the numerator, but also squaring the denominator. We're squaring the numerator. Sorry, I wanted to do that as just the y2 minus y1 in parentheses over 2 squared. All right, just to show you that there's more than one way to work out problems like this, I'm going to go ahead and factor out a 1 over 2 squared, and then have x2 minus x1 squared plus y2 minus y1 squared. So now this is the square root of 1 over 2 squared. 1 over 2 squared is 4. Oh, sorry, 2 squared is 4 times the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, that's kind of nifty because the square root of 1/4 is 1/2 times that expression we originally got for the length of segment PQ. So to sum it all up, what do we notice? Not only is MQ half the length of segment PQ, they're both the same, but segment MQ has the 1/2 in front, but segment MQ has the exact same length as segment PM. So that's what part D is asking us to think about. Compare PM and PQ and compare MQ and PQ. Well, we already saw that segments PM and MQ are both exactly half the length of segment PQ. So since the length of segment PM is equal to the length of segment MQ, the length of segment PM is equal to half the length of segment PQ, and the same thing for the length of segment MQ. That's how we've proven that point M is the midpoint of segment PQ. So that's how you do it. That's how you use a coordinate proof to prove that the midpoint formula is valid. So we're going to do 2 other example problems to help you with the one problem that you're doing on your homework. This is on page 376. This is number 5 on the Check Your Understanding. So it says the coordinates of 3 collinear points. Ooh, that's a good vocabulary word. That's saying that points M, N, and X lie on the same line. And they give us the coordinates right here. So to show that point X is the midpoint of segment MN, what do we need to prove? Well, we need to show that point X is halfway between points MX and XN. That is, we need to show that the length of segment MX is equal to the length of segment XN. So really quickly, we can sketch out why we're saying that's true. So let's say here's our y-axis, here's our x-axis, and let's say these 3 points all lie on the same line segment. So here's point M, here's point N, and here's, so this is the x-axis, but this is point X right here, okay? Well, since these 3 points are all on the same line, if we know that these 2 segments are the same length, that'll guarantee that segment, when we say these 2 segments, segments MX and segment XN, if these 2 segments are the same length, then point X has to be the midpoint. If they were not collinear, like if point X was out here, then just because MX and XN are the same, that doesn't guarantee that point X is the midpoint. So in part C, we'll have to think about that situation. But since we know that point X is somewhere on this line segment, X will be the midpoint if it divides segment MN in half, and that will be true if the length of segment MX is the same as the length of segment XN. Okay, how do we go about proving that? Well, we're going to set this up the exact same way as we did in number 3, the last example that we worked out, okay? So we're going to first work out the length of segment MX, okay? So we're going to do that with the distance formula. We're going to plug points X and M into the distance formula. I'm going to go ahead and put in the X coordinate for point X first. A plus C divided by 2 minus the X value for point M, A. The difference in the X values plus the difference in the Y values. And that needs to be squared. Okay, so all we need to do is simplify this out. Just like we did before, we're going to do a common denominator. Common denominator for the first term is 2, so we want to have a common denominator of 2 for the second term. But remember, this whole difference is squared. Same thing for the difference in the y coordinates. Common denominator of 2, so now that's 2b. Okie dokie, well, we can now combine these, like these 2 terms right here. We're subtracting fractions, the denominators are the same, so we can combine those into a single fraction with a denominator of 2. A minus 2a is negative a. I'm going to put that second though. We've got positive c left over. So that's c minus a divided by 2 squared. Same thing happens over here. The d is positive. B minus 2b is negative b. All right, and we've seen this several times. We're going to square this 2 in the denominator. So I'm going to go ahead and make that be c minus a squared over 4 plus d minus b squared over 4. All right, so now we can factor out that 1/4. And when we take the square root of 1/4, that's going to give us 1/2 of the expression square root of c minus a squared plus d minus b squared. Now, we've seen this several times. If you work this out, when you plug points x and n into the distance formula, you're going to get the exact same thing. I'm going to leave that for you to work out and check. So that shows us, since we have the same expression for segment xn and segment mx, that shows us that those lengths are the same. So that guarantees that point x is the midpoint, because those two smaller segments are exactly the same. Now part C says, suppose you did not know that the points were collinear. Show the additional work that you would use to prove that point x is the midpoint of segment MM. Well, now we would need to work out the actual length of segment MN, which would really be pretty easy because we don't have any fractions. So let's label our coordinates here, x1, y1, x2, y2. So that's going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, if we just compare this to what we had for xn, like xn is the same thing as what we got for mn, it's just it doesn't have the 1/2 in front. Same thing when we compare the length of segment mn and the length of segment mx. This is the length of segment mn, but mx is half. So what we've shown is that the length of segment mx is half the length of segment mn, and the length of segment xn is exactly half of the length of segment mn also. So that would only be true if x were the midpoint. If point x were way out here, then mx and xn could be the same, but the length of mx would not be exactly half the length of segment mn. That proves that point x is collinear with m and n, and therefore is the midpoint. All right, last one. Now this is really going to help you on number 1 on your homework. I'm just telling you. So if you get stuck on the homework, feel free to come back and look at this. Given that points P and Q lie on a vertical line, write a coordinate proof to validate the midpoint formula. So let's draw a picture for this one too. So we've got an x-axis, a y-axis, we've got an x-axis. So here's our x, here's our y. So it's saying that they lie on a vertical line. So let's say here's our vertical line. Here's point P, here's point Q, and here's the midpoint. Well, one thing you should notice right away is that since this is a vertical line that points P and Q lie on, the x values are the same, right? So we know that the x value for the midpoint is going to be the same. So the first thing that they want us to do is substitute the coordinates of P and M into the distance formula. Well, when we do that, we're going to get, let's see, x2 minus x1. But x2 and x1 are actually the same, so that'll be interesting. Plus, let's go ahead and do y1 plus y2 over 2 minus y1, and that's supposed to be squared. Well, the good news is this just goes away to 0, right? x1 minus x1 is 0. Okay, so all we need to do is simplify out this expression. That's going to be, like we've already seen several times, we want to get a common denominator. So that's going to be minus 2y1 over 2. That whole expression is squared. All right, so cleaning things up here, we've got a 2 in the denominator. We've got y2 in the numerator. y1 minus 2y1 is negative y1. And so we can leave the length of segment PM as this expression right here. They want us to do the same thing with the coordinates of points Q and M. So we're going to do the length of segment MQ. Very, very similar. X1 minus X1 is still going to be 0. So I'm just going to skip to writing this out right here. It's going to be the square root of y2 minus y1 plus y2 over 2. That whole thing is supposed to be squared. Well, we want a common denominator. So that's 2y2 over 2 minus y1 plus y2 over 2. That whole expression is squared. And so now 2y2 minus y2, that's y2 on the top, minus y1 over 2, and that is squared. So what we've shown so far is that the length of segment MQ is equal to the length of segment PM. So that's half of it, but now we want to show that the length of segment PN is half the length of segment PQ. So let's work out the length of segment PQ. So the length of segment PQ, let's see, that is going to be, well, if we plug in x1 and x1, that's going to be the square root of x1 minus x1 squared plus y2 minus y1 squared. Hey, that's pretty nice because x1 minus x1 is 0. That's going to go away. So the length of segment PQ is just y2 minus y1 squared. Well, we've already seen this trick several times. To show that the length of segment PM is half the length of segment PQ, we want to turn this into a fraction, y2 minus y1 squared over 2 squared, since we're squaring the numerator and the denominator. But that's really equal to the square root of 1/4 times the square root of y2 minus y1 squared, which is really equal to half of the square root of y2 minus y1 squared. So this is your first splash into coordinate proofs. For the next proof, we're going to do proofs about slopes in activity 26-2. Thanks for watching.